Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. Today we're going to look at one of the questions that my district put out to our 7th grade students for their first week of remote learning. And it was relating the wheel of a remote control car and the speed of a remote control car to an actual car on a freeway. So, I want to give you an example that you can use to help you think about the problem you have at home or relate it to another problem that you have around you in your life and see how you can blossom mathematical learning from the comfort of your own home, with your inner teacher, with everything that you already know, because you have everything you need to be successful, and it's about how you show up and how you listen to others and how you struggle and embrace the struggle in order to learn. So my daughter, you can see her in the corner of your screen riding her tricycle. Okay, this is her tricycle. And she loves this tricycle. We push her around in it, and soon she'll be able to pedal herself. But right now, when we put her in it, we can let her go down the driveway, and she's pretty fast. So she can travel about 115 inches in 2.5 seconds. It's kind of a random measure. Her trike wheel, she has 2 different size trike wheels. So which one would I really want to consider? The back wheel has a diameter of about 6 1/8 of an inch. The front wheel is much larger. What we want to do is compare the speed of Rosa on her tricycle to the speed of a car on a freeway. So we need to say, what information are we given? We're given that the diameter of her tricycle wheels are about 6 1/8 of an inch, which gives us a circumference of about 19 1/4. And all I do for that is I multiply the diameter by pi, right? Our favorite ratio. Okay, circumference equals diameter times pi. So here I got the circumference is about 19 1/4 because 6 1/8 times 3.14. Well, let's just estimate. 6 times 3 is 18. So it makes sense that a little bit more than 6 and a little bit more than 3 is about 19. So we have a circumference that's close to 20. We have a diameter that's close to 6. And how does that relate to how fast the car is traveling? I don't know. Let's see. So if Rosa can travel 115 inches in 2.5 seconds, her speed, her rate of change, okay, I like the purple marker better. I'm going to switch back. Her rate of change, her average speed, is we often do the distance divided by the time. Okay, distance divided by time. So here she traveled 115 inches in 2.5 seconds. So we can get the unit rate here. What's her average distance per 1 second? And I love using tools in mathematics because arithmetic is a good thing to practice, but it's not all of math. So in this situation, I'm problem solving. So I'm going to use a calculator to help me get the calculations done quickly so that I can get the bigger picture of the problem at hand done more rapidly and not have to hold myself up with hand computation. There's space for that in mathematics, practicing, finding the structure in our number system. But here we're just going to use the calculator. So we have 115 inches in 2.5 seconds. I divide them to get the unit rate. Okay, I can just divide 115 divided by 2.5 and then put that all over 1, which gives me 46 inches per 1 second. Okay, so she is traveling about 46 inches per 1 second in our driveway, and I will get out of your way. So that's her speed. Her speed or her rate is 46 inches per second. And I wrote IPS because when we're comparing this to a car on the freeway, cars travel at miles per hour or kilometers per hour. When I lived in Costa Rica, it was kilometers per hour. So here we want to compare the speed of Rosa on her tricycle to a car. So a car on the freeway, I I'm going to say is that the average speed of a car on a freeway is going to be so different. And in a traffic commute, like on the way to work from Cape Cod to Boston, that traffic goes bumper to bumper, slow, slow, slow. But in the middle of a day in the freeway, going to P-Town on Cape Cod, hey, I think that us New England drivers are going faster than 60, but let's say it's 60 miles per hour. We want to see, is Rosa going faster than a car? If she's going that fast, 115 inches per 2.5 seconds or 46 inches per second IPS, how does that compare to a car on the freeway? So do we want to rewrite Rosa's speed in miles per hour, or do we want to write the car's speed in inches per second? I'm going to do it one way. I challenge you to do the other and see if you get a similar result. Okay, so if I want 60 miles per 1 hour and I want to convert it into inches per second, okay, first I want to find a conversion rate that'll cancel out the hours. So I know that if I multiply 1 hour by something divided by an hour, these two will cancel. And I know that 1 hour is the same as 60 seconds. So 1 hour divided by 60 seconds, that's the exact same thing. This equals 1. So it's like when we're finding equivalent fractions, like 2 over 3 times 5 over 5 is still 2 over 3. Because 5 over 5 equals 1. So it's just rewriting an equivalent expression, an equivalent numeric expression in fraction form in another way. So when I multiply 60 miles per 1 hour by 1 hour over 60 minutes, not seconds, I hope you caught that mistake. Okay, that's not changing the value of this ratio at all. It's just reformatting it into a different visual. It's like putting on a costume. It's the same person, you just look different. Okay, so then we still need to multiply, these will cancel. 1 hour and 1 hour cancel, they cross cancel, and now I have minutes, but I want seconds, I don't want minutes, so now I need to do it again. I need to multiply 1 minute over 60 seconds. So then I get miles per second. But look, the 60 and the 60 didn't cancel. It's just the units of measure. So now I've canceled out hours, I've canceled out minutes, I'm left with seconds. So that I know that the miles per second is 60 divided by 60 times 60. Right here I have this 60 in the numerator and then two 60s in the denominator. And now I'll cancel, because 60 divided by 60 is 1. And then I have 160 left in the denominator. So now I know that the car is traveling 1 mile per 60 seconds. Pause and ask yourself, does that make sense? If a car is going 60 miles per hour, does it make sense that it's going 1 mile every 60 seconds or 1 mile every minute? Does that make sense to you? Okay, so now we're still not done because Rosalie was traveling at a speed of inches per second, not miles per second. So I still need to convert this into inches per second. So what I need to do is get rid of the miles. So 1 mile, I want these to cancel. I want the unit of mile to cancel. 1 mile, I have my conversions here, is 63,360 inches. Okay, my miles will cancel and I'll be left with inches, which is what I want, and seconds. So I get 63,360 inches in 60 seconds. So I have the units of measure I want. Now all I have to do is simplify 63,360 divided by 60. And that's 1,056 inches per 1 second. Because all I did here was I did 63,360 divided by 60 to get 1,056. Okay, so who's faster, Rosalie or the automobile. And yes, I think you were right. I think you probably guessed right that if she's about 50 inches per second and the car is going about 1,050 inches per second, how many times faster is the car than the baby on the tricycle? Well, 50 goes into 100 twice, so 50 goes into 1,000 20 times, and then one more, so 21. So about 20 times faster is the car than the baby on the tricycle. I hope this helped you do the remote control question, movin' and groovin', for week 1 on the remote learning assignment for Barnstable Public Schools. I did it a little bit differently so that I didn't give you the answer. I just gave you sort of a platform and a structure to find an answer that you're proud of. The second part of this whole activity was saying, how could an advertiser, use these calculations to say, this is traveling faster than life, right? Well, if you put things in her speed is 46. If you leave out the units of measure, then somebody might think, that 46 is miles per hour. Wow, my baby can go 46 miles per hour on her tricycle. That is wild. Let's get it. Okay? Or you could start playing around with any other way to sort of manipulate it. And I don't think that I would buy a tricycle for my baby if it was going that fast. But maybe if this was about a remote control car, which is what the original task was about, then you might want your remote control car to go super, super fast. So we were given extra information in the beginning too. We were given information about a circle and the diameter of the wheel, and we didn't actually have to use it. Can you think of a problem that you could investigate regarding this information using the relationship of a circle to its diameter? What would we need to know about the actual car? What's the diameter of a wheel of an actual car? Does that impact how fast something goes? The revolution of a wheel compared to the speed of the object? I don't know. I hope you follow your curiosities and take a look. Thanks for tuning in. As I have time, I will present more quick structure-like explorations of tasks that we're posting on the Barnstable Public Schools site so that students can find some doors to open into problem solving and close those if they don't fit for you and open another one, because there's so many different ways in solving one problem. When the 4 7th grade math teachers were on a conference call about this last week, we all had different ways of doing it. I encourage you to post your way of doing it to your Google Classroom, share with others, find a group of peers that you can collaborate with, because mathematics is a human subject and you can only learn it deeply with others. So that's either people in your home with you or virtually, remotely with peers and collaborating and listening to each other. Thanks again. I'm so excited to be able to bring this to you. I'll see you soon. Signing off.